When working hot metal, like a steel bar, it's very important to remember that after shaping, it's by no means fit for the job. Take this chisel. It's being forged into shape by a traditional method. But before the chisel can be used, it must be heat-treated. This is done by heating it and then quenching it in water. This hardens the chisel, but unfortunately, it'll also make it brittle. So brittle that if it's used without further treatment, it'll break. It needs not only to be hard, but tough as well. It has to be tempered. To do this, the smith cleans the surface of the chisel with an abrasive paper and then reheats it, this time to a lower temperature. Then he quenches it in water. This makes the chisel less brittle, but it also robs the metal of some of its hardness. To show you what happens, let's look at a small carbon steel rod. The rod can be flexed easily in the hand, and you can see how elastic it is. When the rod is heated in a furnace to red heat, then cooled as quickly as possible in water, it will become hardened. So hard, in fact, that a file won't make any impression on the surface. It'll just skid over it. But unfortunately, the rod has now become brittle. In this second experiment, an identical rod is heated in the furnace to the same red heat. Then it's cooled very slowly by immersing it completely in vermiculite, a process known as annealing. The metal will now have good ductility and will be soft. You can mark it with a file with no trouble at all. It'll also bend easily, but after bending, lacking elasticity, it remains bent. In a third experiment, the rod is again heated to the same temperature, and then it's quenched rapidly in water. That makes it hard and brittle, just as in the first experiment. Then the rod is put back into the furnace, and this time heated to a lower temperature. After this, it's cooled slowly in vermiculite. It could also be cooled in air. This process of heating and cooling is known as tempering. It's a carefully controlled compromise between toughness and hardness. The rod doesn't mark too easily with a file, and it can be flexed in the hand. The extent to which any steel may be hardened is largely dependent on its composition when it was made in the furnace. The amount of carbon present is most important. Sometimes the addition of transition elements, such as chromium, can also affect its behavior. In fact, adding such elements produces what's known as an alloy steel. But it is the amount of carbon present and the rate of cooling of the hot steel which exercises the most influence. To understand how the carbon content and cooling rate affect the steel's properties so dramatically, we need to look more closely at its structure. Let's start with that steel rod experiment. Before any heat treatment, it consists mainly of atoms of iron arranged in a body-centered cube. It's called alpha iron. And there are 9 atoms of iron, 1 at each corner and 1 in the center, which we've shaded for clarity. Under the microscope, it looks like this. Here, there are 2 types of crystals. The rather plain ones are pure iron, ferrite. In the others, the carbon has joined with the iron to form iron carbide, and this combined with the rest of the iron produces a laminated structure looking like mother of pearl. It's called pearlite. When the metal is heated, it reaches a temperature at which the body-centered cubic arrangement changes to the face-centered cubic type, known as gamma iron. We've shaded the central iron atom on each face of the cube. As the rod is heated and the carbon is taken into solid solution, the laminated structure of the pearlite changes. In this form, it's known as austenite. The change from one form to the other is easily reversible. From the high